So still 10 minutes more, sir. I think you will join Zoom, sir.
Yeah, all the time.
சார் மோகன்தாஸ் சார்.
எஸ் சார், சொல்லுங்க சார்.
இன்னும் வரலையே சார் செந்தில்குமரன் சார்.
10:30க்கு ஷார்ப்பா ஜாயின் பண்ணுவார்னு நினைக்கிறேன். ஐ திங்க்
கால் பண்ணிட்டு ரெடியா சொல்லுங்க. பாட்டு ஜாயின் பண்ணுவோம்.
So let us wait for a few minutes, sir. You know, only 35 participants joined.
Okay, sir. Okay, sir.
Let us wait for some time, sir.
Okay, sir.
I called him by 9 o'clock, sir. He said he will be joining. Confirm பண்ணிட்டார்.
யூடியூப் லிங்க் கேட்டு மெசேஜ் பண்ணிருந்தாரு.
Oh, I see. Okay, okay. நான் சொல்லியிருந்தேன் அவர்கிட்ட. Please make use of YouTube link also to view the queries at the end of the session சொல்லிட்டு.
ஆமா சார், யூடியூப் லிங்க் மெயில் பண்ணிட்டேன் சார் அவருக்கு.
Okay, okay. Thank you. Please at the end of the session.
ஆமா சார், யூடியூப்
Sir, very good morning, sir. Speaker has joined today. Sir, switch on your mic, sir, actually. Yeah. Yes, sir.
Yeah, can you
Yeah,
hear?
yes, sir. Yes, sir. Very good morning, sir.
Good morning.
Good morning, Sendhilkumar sir. Ramesh Babu, HOD Mechanical sir.
Hello, sir. How are you?
Fine, sir. How are you?
I'm doing good.
I also attended your program at SI Engineering College with respect to the 3D printing for for manufacturing the COVID equipment. It was very interesting.
Okay. Sir, shall we start, sir?
Yeah, so I will start sharing my screen. So,
Okay. Before that, let me deliver my introduction and welcome speech, sir.
okay.
Yeah. Very good morning to all. I am Dr. Mohan Das, Associate Professor in the Department of Mechanical Engineering, Sri Venkateshwara College of Engineering. Myself and my colleague, Mr. A. Kumarasamy sir, organizing this webinar on 3D printing and mass customization in manufacturing on behalf of Department of Mechanical Engineering, SVCE. And it's my pleasure to extend a cheerful welcome to you all. And my warm welcome to our head of the department, Dr. S. Ramesh Babu sir, and today's guest speaker, Dr. Senthilkumaran sir. Very happy to getting connected with wide participants through this webinar on 3D printing and mass customization in manufacturing. And this webinar aims to address questions on the current status and future developments in the additive manufacturing through 3D printing. Now, I would like to request our head of the department, Dr. S. Ramesh Babu sir, to address the participants.
Thank you, Mohandas. Respected Chief
Yes, sir.
Guest, Dr. K. Sendhilkumaran, faculty member from IIITD, who is specialized in additive manufacturing, sustainable manufacturing, and smart manufacturing. So I think I have to thank the coordinators at this time because they identified the apt speaker for this, today's session. So in this regard, a special thanks to Dr. Mohandas and Mr. A. Kumarasamy. On behalf of Mechanical Engineering Department, on behalf of Sri Venkateshwara College of Engineering, and on my own behalf, I welcome Chief Guest Dr. K. Sendhilkumaran for this webinar on 3D printing and mass customization in manufacturing. Warm welcome to our coordinators, Dr. M. Mohandas and Mr. A. Kumarasamy, and also warm welcome to all the participants. Because brochure was floated, I think there was a very good response. Because this being a key area in today's scenario. Okay, so we had more participants and response for this program and all. I take privilege in explaining a few features of our department. Kindly bear with me. The Mechanical Engineering Department was established in the year 1985, moment when the college was established. The department offers one UG program, that is Bachelor's in Mechanical Engineering, which is accredited by National Board of Accreditation since 1998. And we have two PG programs, one in mechatronics and the other one in industrial automation robotics. The second one, which I mentioned, that is the industrial automation robotics. We are waiting for the approval from IIITD. I think we have a positive response from them. And we starting this course in this coming onwards. And the Department of Mechanical Engineering is research from Tamil Nadu have registered in our research center. At this moment, I wish the K. Sendhilkumaran, who is one of our advisory committee member in recommending the syllabus for industrial automation robotics. We are unique in this framing the syllabus for industrial automation robotics. In what way we are unique? That is, we have framed the subject content in such a way it should be the current industrial scenario. So, okay, all the and if you see the syllabus, if you see the subjects, okay, all the subjects will be covering the key elements of Industry 4.0. Okay, so all the subject of Industry 4.0 will be dealt with, and also we have been focusing more on laboratory part also. Hence, the students, the aspiring students, okay, who are in the final year, who want to pursue their masters, okay, and the eligibility criteria for joining this course For more details about the program, what is it, the eligibility criteria, you can see or visit our website, that is www.svce.ac.in. And coming to this workshop, the 3D printing is one of the most stressed course in the current manufacturing scenario. Okay, you might be knowing that the importance because when I started one course on 3D printing in Coursera, I found that that is many in US have built the own 3D printing for manufacturing certain components. And even that is at the end of this today's section, you can see that our expert member has fabricated his own 3D printing in his in his workshop. Okay, and the thing that he'll be as more aspecting today, okay, who can teach you a lot of respect to the fabrication of 3D print and so how because we are printed house and another 2 or 3 years, okay, we'll be having a small 3D 3D printer in our each and every house, okay, so that if you want to make any customized object and all, which can be done, okay, on your own. Okay, this is going to be a scenario, and this is a small thing about which I know about the 3D printing, and the more detail about the 3D printing, about its importance will be dealt by Dr. SENTHILKUMARAN. So with this small word, I express my sincere thanks and also wish the participant all the best. Thank you, sir.
Thank you, sir. Thank you. And it's a great honor for me to introduce today's speaker, Dr. SENTHILKUMARAN, sir, who is working as a professor in the Department of Mechanical Engineering, Indian Institute of Technology, Design and Manufacturing, KANCHEEPURAM. Dr. SENTHILKUMARAN, sir, did his PhD in the field of additive manufacturing from IIITD Delhi, and he worked as a guest researcher in the Systems Integration Division of National Institute of Standards and Technology, USA. He has published more than 15 articles in the field of additive manufacturing in high-impact journals. And SENTHILKUMARAN, sir, is the head of the additive manufacturing laboratory at the IIITD. And apart from that, he is the coordinator of Teaching Learning Center of IIITD. With this brief introduction, let me hand over the session to Dr. SENTHILKUMARAN, sir. And I request all the participants to unmute your speaker and switch off the camera. And if any queries, please make use of the chat box. Thank you, sir. Let me hand over the session to Dr. SENTHILKUMARAN, sir. Sir, I think you have to switch on the microphone, sir.
Am I audible to everyone now?
Yes, sir. Yes, sir. It is audible.
Okay, thank you. So, good morning, everyone. So today we are going to talk about a few topics on mass customization. In addition to that, there are other topics that I will be also discussing along with this topic. One of the important things that I wanted to tell you today is, like, first of all, I want to thank Sri Venkateshwara College for giving this opportunity to interact with all of you, because in the unprecedented situation right now we are going through, especially in the COVID-19 situation. So the learning has not stopped. So we have been using all the online tools to learn so many new things. Hopefully, if you have attended some of my previous sessions, you might have a bit of knowledge about what mass customization is and what 3D printing is and about my work. So since already there's a good amount of introduction being given, so I'll just quickly go through my presentation. So it would be very useful then to spend most of the time there rather than having some introductory slides. So to tell you briefly about my work. So I actually work on 3D printing. So my additive manufacturing is one of the areas, and also I work on smart and sustainable manufacturing. And the research and consultancy, we have established a lab called Design for Additive Manufacturing Laboratory. And we also run 2 programs, which I have been coordinating right from the inception. So the BTech and MTech Smart Manufacturing programs. And also for the outreach, as Professor Mohandas mentioned, that I'm also the coordinator for the Teaching Learning Center, where we have a makerspace where people can come in and make affordable, low-cost, do-it-yourself type of machines for the laboratory use. So it's like the educational technology development using 3D printing and other CNC tools. So it's like 3D printers that makes another 3D printer. So it's like RepRap type of concept. But we are going ahead with more than 3D printing. We have laser scanners and laser engravers, 3D printers, and even some chemistry equipments. So whatever laboratory equipments which involve certain level of mechatronics knowledge, we will be able to help you. So that is the TLC. So yeah. So to start off with, I would like to show you the AM ecosystem. So if you look at the AM ecosystem, so there are a lot of I would say companies which are interested in this particular aspect of AM. So for example, if you look at UIS machines, and there are metal machines, there are ceramic machines, there are electronic 3D printing machines, and there are software which supports this. So if you look at the industry, 30 years ago, 3D printing is nowhere. So in last 3 decades, this technology has grown a lot, and right now we are seeing industries adapting faster than ever. So additive manufacturing has been one of the key turnkey technologies for many additive manufacturing industries, especially for 3 reasons. One is to cut cost, second is to remain more efficient, and third one is to introduce a new product into the market. So these are the 3 areas in which additive manufacturing really fares well. Now, I have a certain notion when I say 3D printing is being adopted very fast in industry. That's because of there are various developments that have taken place. For example, materials is one, especially, and there are science. Like for example, materials is one, and then we have process, and then we have science, and then design. So today I'm going to talk more about design rather than materials, process, and science. We do a little bit of work on materials as well as in science, but yeah, in process as well. But today's topic is more related to design. So if you look at, there are a variety of, I would say, tools and techniques that people use to bring, let's say, for example, a part which is to be manufactured into reality. So it starts all with the digital CAD model. So I'll just quickly, yeah. So it all starts with the CAD model. So the CAD model is first created, and then it is tessellated. This is just general introduction to people who don't know 3D printing. And then there's a part fabrication and there's a part finishing. So this is the various steps that is usually taken care by the additive manufacturing. And then we have several kinds of process in additive manufacturing, which are classified as 1D channels, 2D channels, an array of 1D channels, an array of 2D channels. So right now, so when we look at the basic steps, the first step is, as I said, to create a 3D model. And the second step is to tessellate it. And the third step is to slice it. Tessellation is an intermediate step where you actually convert the 3D model into a coarse model. Just so just to basically give you an idea about how you can actually slice the CAD model. So there are part fabrications. After you slice the model, then the part needs to be fabricated. So the part needs to be fabricated by slicing the geometry, right? So now once we slice the geometry, then individual layers are going to be manufactured. Either I think someone else is starting the presentation, so it is better that all of you need to be restrained. Don't present. Okay, so don't present your slides. Okay, thank you. So if you have any slides to present, maybe you can take it to the last. Okay, so I think some of you are trying to present it. So I think the coordinators can just pass on a message that don't try to take the presentation slides. Okay, thank you. So next is part finishing. So the part finishing aspects is like once the part that we directly get from 3D printer is sometimes far from perfect. So sometimes what happens is like we try to basically get a part, but the part may not really, I would say, not up to the mark or not up to the specifications, or it's like not within the upper and lower specification limits. So essentially, it has quality issues. To improve the quality, you may have to take it through some post-processing operations. There are a variety of post-processing operations that it can be done. So this is a general overview of any 3D printing. So there are many different names. So some of the names is like think yeah. So yeah, I think I am presenting. I think I'm able to see the screen. Are you able to see the screen? I'm getting a lot of messages. Or is it possible to mute the chat messages? Probably yeah. Okay, so fine. So I think we have this part fabrication. Once it is done,
Sir, just a second, sir. Just a second.
Okay.
Sir, just a second, sir. Sir, dear participants, please unmute your microphones and switch off your cameras. Don't share your screen. Don't disturb the presentation of our speaker. All of you, please switch off your camera. Mr. Prem Kumar, Mr. Matthew KK, switch off your cameras.
see, when you are trying to present, my screen will go away. That is the reason why you are not able to see my screen.
Mr. Prem Kumar, switch off your camera.
See,
Mr. Matthew,
the operators can do it.
camera. Yes, sir. Please, sir.
Okay, so this is the slide that you have right now you have seen. So in this case, for example, you have the 1D channels. Probably I will also tell you a brief background on this classification. This comes from Professor Ian Gibson. When you have the layers needs to be fabricated one at a time. So the layers can be fabricated by many different variety of ways. For example, one of the ways is to do a 1D channel or a 2 into 1D channels, or array of 1D channels or a 2D channels. For example, here, so this is the 1D channel, this is the 2D channels. Why we need to do this? For example, sometimes you have a technology wherein you can print the entire layer. So but you can, in some technology, you can only print only one strand at a time. So there are technologies which could print the complete layer. There are technologies which could only print, I would say, an array of 1D channels. So in order to effectively, I would say, to classify them, so you have many starting materials, like you have a liquid polymer, you have discrete particles, you have molten materials, you have solid sheets, but you have different kinds of technologies. So what happened is that the ASTM told that there are too many acronyms, like you see stereolithography, SLEA, selective laser sintering, SLS. There are so many different types of processes. Almost there are 50-60 processes which are there for last 30 decades, and 5 of them are commercially successful. So ASTM said that we will try to classify, we will give them generic names. So this is what the generic names that have been given to the 3D printers. So in this, if you see, for example, the first one is wet photopolymerization. So wet photopolymerization, what we do is we typically take a wet and then there's a liquid filled in it, and there's a laser which comes from the top and then scans the liquid layer and then fuses the particles together. In powder bed fusion, you take a layer of powder, put it on a platform, and then the laser comes in from the top and consolidates the powder particles selectively wherever you need to basically fuse the particles together. So that is powder bed fusion. Material extrusion is like an extrusion process where you have a what you call as this nozzle, which is a heated liquefier, and then there's a 2 pinching roller which takes the filament. So the raw material is in the form of the filament. The filament basically comes in and then fuses. I would say the fused filament is going to be deposited, just like a jalebi where you're squeezing or making a muruku or something like that. So it's like you're squeezing the material and making a layer. And then you have material jetting. So essentially, which is like a normal your HP, you have inkjets and laser jets. Very similarly, like an inkjet process, you have a material which is in the resin, and then you are just jetting. So you use the same type of technology which you use in inkjet printing. Here, the material is not an inky, but it is going to be a resin. So the resin is going to be jetted onto the surface by using something called as, there's very similar names there, called as a, let's say, a pump, or sometimes it's called a cartridge. So you have what you call as this, drop on demand type of techniques, where the droplets of resins are going to be deposited on top of a layer. So you have several of these techniques. So binder jetting is another technique wherein we use, I would say, the fused powder particles, where the powders will be fused together by binders. So the binders could be either aqueous binders, or it could be the binders could be typically coming from, let's say, a resin-based binders, or it could be thermally cured. Sometimes you can cure it using a polymer which could be cured. Right. So there are so many things like binder jetting. Sheet lamination is like laminating one sheets of metal or, let's say, polymers into it. So direct energy deposition is another technique where you are going to deposit one layer of material. So it's a nozzle, coaxial nozzle, where the laser comes in from the center of the nozzle and then the powder gets deposited around it. So all these techniques are together called as 3D printing or additive manufacturing technology. In the ASTM classification is usually like this. Okay, so now we are going to the design part of it. So I think this is a very important quote, which I would like to basically tell you. So Albert Einstein said the best design is the simplest one that works. So that means you have a design, but you need to make it more simple as possible. So that is the idea. So that is the notion. So we call this as this principle. Probably you must have heard about it. Keep it simple, stupid. So now what this means is like when you are designing something, you always keep it so simple, so that there are many advantages that you get out of it. So maybe you have something like so you have a design which is to be manufactured. Either it is going to be very costly during the manufacture, or sometimes what happens is that it may not be manufacturable at all, or there can be some constraints. For example, tool cannot reach, or the part cannot be taken out of the mold. So there are a lot of issues with the design when you are making it complex. So the notion of simple design is to basically address the issues in cost, maybe even the usage. When you are using the product, it's so simple so that it becomes easy to service and things like that. So then it gets complex, even the design for manufacturability, design for assembly, design for serviceability, design for quality. So all this design for X, so for we call is going to be really difficult. Right. So in order to issue this, kind of, I would say, in order to solve this issue, what people did is like they simplify the parts. So if you look at the design procedure, so how people start designing components. So these are before the 3D printing era. For example, anything which is we call as design, it exists for undersurface. For example, like Ford cars have been manufactured the last 100 years. So you have designs which have been made, parts which have been made, but the 3D printing, before even the 3D printing era, the way the people do design is that it's a cyclic process. People start with some design, and then they research the problem, and then imagine and develop a possible solution. Then they plan and select a promising solution out of many solutions, and then they build a prototype to test actually how the design works, and then they improve as and when they need. So this is, I would say, typically a process, a cyclic process. Sometimes they are also called as waterfall model because the one step goes in the next step and the next step and the next step. So it's like you have a sequence of steps. So now if you see, so you have a plan, you have a develop, and then you construct, and then define, and then prepare and document, and finally do the distribution. So, but it's like a cyclic process. So it's a cyclic process where you develop, select, build prototype, and evaluate prototype, and again research the problem. So to address this issue, so to understand this cyclic issue, one of the things that we should start looking at is like, is it possible to do concurrently? So is there some steps can be concurrently done? For example, some manufacturing testing can be done concurrently and things like that. So there are a variety of tasks which could be done concurrently. So, but one of the issues is like when you have, so when you have a product, so what happens is that when your cost of design is like very high, and the cost of production is also very high. So let's say, for example, this is design cost, this is production cost. Now, what happens is that if you see, for example, when you have spend little amount of money in the design, you spend a lot of amount in the production, but you are able to basically spend a lot of amount of design, the cost of production comes to. So essentially, what this tells you is like if you spend more time on design, catering to the needs of the manufacturing, or addressing the issues early on, so your production cost can be minimized. So essentially, it says that if you are able to bring some of the decisions very quickly early on, so that you can eliminate the problems which you would otherwise undergo at the later stage. So this is the idea. And so here comes the topic. So when we are discussing about one of the important topic is mass customization. So what we call as customization, and what is called as standard and one-off design. Now let's just look at this. When we look at cost, we also look at time. So if you look at the World War, during the World War time and previous time, so there are many standards that have been developed. If you look at the entire world is made up of standards, like your building that you're sitting on, right? So the Bluetooth that you are using, right? So the IEEE standards. Then you have building codes, Then you have mass, time, and other standards. You have standards for exchange of CAD model like step files, IGS files. So you have standards everywhere. People make standards to make life easier. So similarly, people make standard designs. For example, if you want interchangeability in your design, let's say you want to buy a nut here and bolt in in another continent, you can even assemble it together. Meaning that there is an interchangeability. Meaning that if you are standardizing your design, you are able to basically replace it very quickly. Your availability becomes very large. So the standard designs have been there for a very long years. People are able to make standard designs just because they help, I would say, in interchangeability. It helps them to basically address the cost issues as well as availability, serviceability, and all those issues. So if you look at here, this is a standard design. So this is a production cost. This is a setup cost. In a standard design, your entire cost goes in production, whereas setup cost is very, very less. Whereas if you are using a one-off design, your production cost and setup cost becomes extremely, I would say, high and also equal. So meaning that your production cost for a standard design occupies the largest cost. Whereas your one-off design, let's say one-off design means is something like you are making only one piece or only two pieces. So essentially, if you are looking at the conventional manufacturing process like stamping or a car manufacturing or maybe injection molding or any for the matter of even machining. For machining, you need jigs and features. For injection molding, you need what you call as the mold. For stamping, you need a die. So essentially, making this die is very costly process. It's a lengthy process. Making a fixture is another lengthy process, right? So when we are trying to basically address this cost involved in these aspects, only if you hit a volume, let's say if you are selling more volumes of it, then only you can justify the cost. So essentially what we are talking about here is if you are making designs which is very unique, means like only one design, that means you are going to incur a lot of cost in conventional manufacturing. That's the idea of this thing. Now, so very similarly, if you break down that cost into even much more, I would say, further cost, like you have a labor cost, you have a factory overhead cost, you have a development cost, you have a material cost, you have a testing cost. For a standard design, the total cost is very, very less. Whereas for the one-off designs, so you have special tests to be done, you have materials to be addressed, you have development issues, you have factory overheads, you have technology overheads, design overheads, labor costs, so everything increases. So conventional manufacturing process like injection molding and everywhere, if you are making designs which is really unique for every customer, you're going to incur a lot of costs. This is the background intuition that I want to convey. So what I'm trying to tell you here is if you are taking a standard design and if you are taking a one-off design, the standard design is going to become cheaper over time. So when you hit the volume, you are going to get the cost benefits. Your cost gets amortized, so your total cost gets reduced. Whereas the one-off design, let's say you have a design which is uniquely manufactured, right? So then it is going to be very costly. This is about conventional manufacturing. Here comes the mass customization angle, which we are trying to talk about today, and how 3D printing is going to help you in that. Now, if you look at here, so this is the mass production and mass customization curve. Now, the one that you see on the top, so this one is called mass production curve, and the one at the bottom, which actually rises to the top at the end of the high volume, is what we call as mass produced. So you have a mass customized and mass produced. So essentially what we are understanding from this particular curve is that if you, let's say, produce very low volume, mass production is going to be extremely expensive. Whereas if you produce very high volume, mass production is going to be extremely cheaper. So it's not going to be expensive, right? But the problem is like people are making widgets after widgets. People are making the same part again and again. But a lot of time, customer may not prefer the same design. For example, I don't know how many of the participants are women here. Let's say you are going to a sari shop and you see all the saris are same. Nobody will buy. So you need different colors, you need different varieties. People can pick and choose one. They can wear one. They can, suppose if you go to a shop and they have only five varieties of sari, but they have the complete shop full of saris. Nobody will prefer. Anyway, you go to a car company, they have only one model, whether you choose or not. So unique designs or standard designs or one-off designs, or I say standardized designs are easy to manufacture. They are cost effective, conventional way. right? So, but what happens is that it is not preferable. So that's why we have this particular region. What we call as when you have mass customization, if you see, this is called the economy of scope. People are willing to pay a little higher. So this is what is called what the price that customers are willing to pay. You see that this is what economy of scale. People are willing to pay even much more than what you actually will do when you do a mass when your design is mass customized. You understand? When your design is mass customized, you are able to basically hit, I would say, volume. At a higher volume, you will sell more and then you will get more. So this is the economic aspects of mass production versus mass customization. Essentially, you see that there's a net value addition here. Even though you are able to at the low volume, means like your volume is going to be low when you are customizing for individuals. Your net, so this is the cost that you are going to basically incur, but this is the price that customer are willing to pay. So you see the profit margin here is extremely high. The gap between this curve and this curve, whereas the gap between this curve and this curve is very less, meaning that even if you are able to basically spend a more, there are some customers who are willing to pay for even more if it's going to be a little costly. But we'll address this issue. But it is going to be extremely, but in conventional, the cost is going to be extremely high. But how to reduce this dollar per unit? This is what is very important. When you are customizing it, your volume is going to hit low. At that volume, how do you basically reduce the dollar per unit or the cost per unit of a particular to be manufactured? So this slide is a extremely good slide with an example. The same curve I'm trying to explain with intervals to the fourth industrial revolution or I 4.4, whatever you call. So let's say you take a car like Model T, which is the second industrial revolution. So when you have a car like this, which is this is the highest mass produced car. I would say the first mass produced car. The highest number of mass produced car is the Beetle car, which is the Volkswagen car. And suddenly you see that after 2000, people started decentralizing the production, making it distributed, personalized, and manufacturing of complex products. So essentially, what we are trying to address here is the issue that we are moving slowly from mass customization, mass production to mass customization. Essentially meaning that we are trying to basically make a lot of unique parts or one-off parts than a standard design. So the 3D printing actually reduces the cost if you are making only one part. Let's say you take a simple design, you want to take it through stamping process, then you have to send a die, make a die and then make a component and do it. Whereas if you are using 3D printing, you don't have to make a die. So it's a die-less manufacturing process. So it reduces the cost. Even you can actually hit the complexity also. You can make more complex, right, more customized and less cost for individual parts or single parts. So conventional manufacturing may be a little costlier for this type of an application. That is why 3D printing is taking a center stage. 3D printing is considered to be helping the mass customization angle. And also today we are, yesterday I think someone mentioned about the last webinar that I gave on COVID-19 also, 3D printing, how 3D printing helps COVID-19. One of the issues with the manufacturing is like everything is in China. Now you're not able to get the parts from China because it's centralized. The manufacturing is centralized in big factories in China, and we are not able to, do the logistics and supply chain disruptions happening. So that is because of this, we are able to basically see a disruption and disturbances in the supply chain and production, as well as making the components. So if you have 3D printing, you can decentralize them. So you can put printers near to the customers and print them and deliver them wherever instead of making them in a central factory. So 3D printing helps them to decentralize the manufacturing, and also it make it distributed, and also it makes complex products and personalized products. So personalization is nothing but customization. You are able to customize the products to individual needs. So that is the idea. So if you look at here, this is what we call as mass customization. This is what we call as mass production, and this is what mass complexity is. Now let's just look at this particular graph in the next slide a little more clearly here. So what is the mass customization here? So mass customization is about the ability of a design to be customized to individual needs. Let's say, I'll give some examples. Let's say you have a car, and then you go there to the shop, and then you can configure the car for yourself. Like you have RD selector, and you have many other car companies which offers you an opportunity to modify the product to suit your needs. So you have varieties of tools and techniques now available where you can customize the design according to your need. So you have a design, like for example, you go to a doctor. So there is a footwear, and then you want to create an insole. The insole can be basically customized according to your foot geometry. Or I would say sometimes you can also get some components customized according to your personal anatomy or personal geography, or maybe something like it could be customized for individual regions or persons, or it could be customized for applications. For example, there are parts which could be manufactured only once, depending upon what the customer really needs. So they can tweak the design and then fit it to that. For example, implants. The implants has been manufactured. People have been facing a lot of issues with implants. Now implants are custom made. People are able to design something unique to their body, which fits exactly into their body. So dental implants or knee implants and a lot of 3D printed fixtures and things like this. So dental fixtures. So you are able to customize the design and make it very cost effective. That's the idea. Now, so if you look at here, the mass manufacturing where you have high volume, this is what conventional manufacturing like machining and injection molding are really good at. Whereas 3D printing is good at this particular plane. It can actually give the complete manufacturing product. It can actually have a complexity advantage. The design can be more complex. There are 4 different complexities which we are going to discuss a little later. So we can have design complexity, especially called as geometry complexity. We can have material complexity. We have hierarchical complexity. We can also have other types of complexity. So you can build very complex parts. You can customize the parts according to the needs, and also you can actually create, I would say, more volume. So volume at this point of time may be a little difficult with the 3D printing, but over the time when the technologies improve and the process becomes faster, so you'll be able to print more parts and you will be able to build it faster. So that is the idea. So as I said, we run a lab called Design for Additive Manufacturing Lab. In one of the concepts in Design for Additive Manufacturing is like when you have more complexity, when you have standard design, this is the standard design, this is not customized. If you look at here, this is the standard design. In the standard design, when you have design for conventional manufacturing technologies, this is the standard design. It's not customized. So the cost is very low. So, and also if you look at additive manufacturing slightly is not better positioned for these types of standard designs. Whereas conventional manufacturing, you see the costs are lower than the additive manufacturing. But when you are moving the design towards the complexity as well as customization, right? So you see that the additive manufacturing cost doesn't increase, whereas the conventional manufacturing, the cost increases. So this is what we call as the ability of the additive manufacturing to basically address the issues of, I would say, there are 2-3 issues that additive manufacturing effectively addresses. One is the cost advantage, the complexity advantage, as well as the volume or the quantity advantage. All these 3 things can be simultaneously addressed, but volume also there is some little difficulty, but still we will be able to address the volume part little later. But when you hit the volume, it becomes again mass production with the mass design, right? So you understand, like for example, you personalize the product and make it, let's say 1,000 parts, but it is not possible. So right now, so 3D printing is not that cost effective for a very high volume. For niche applications, but for very low volume right now, mass customization could be there. So there are 2 definitions for mass customization that brings a very interesting question. The first definition is, are we able to remain cost effective even at higher complexity? That is one, or higher customization. The way the mass production and mass customization are 2 words are differentiated is, if you are able to take, let's say, a design, right? If you are able to produce in mass production, let's say in injection molding, it every 3 minutes or every 1 minute or even 10 seconds you get a part out. So that is the throughput or production rate at which you work. But 3D printing takes a lot of time. But will you be able to take the same amount of cost for a customized cost as well as for mass produced cost? So mass customization is the ability to produce parts at the cost of mass production. So that is the idea of mass customization. So the mass comes from both volume as well as other cost. So now I will just tell you about a brief idea about what is DFAM. I think the design, when we are trying to basically address the issue, there are always we think design is mostly suitable for, let's say, this particular aspects for particular manufacturing. I think now if you see, for example, one of the idea that we always look at from the design is like, design is mostly restrictive. So we have, even though we say that anything that we can imagine that we can manufacture, but still it's not possible. Many manufacturing processes wouldn't allow you to manufacture whatever you feel. Like for example, you would have seen Ford, right? So Ford cars are nicely proud. Whereas if you see the latest Tesla cars and all, the Cybertruck and all, they are not nicely cropped. The reason is because you have to do a bulletproof vehicle and you have to cold roll. So the cold rolling process will not be the stamping process where you can achieve really good, nice, I would say curved, classy surfaces. Whereas if you see in cold rolling process, you won't get the same nice curved surface. That's why the Cybertruck looks like a big box, right? So that's the reason. So you have a difficulty in terms of the manufacturing that causes the design to change completely. So this is manufacturability issue. This is the issue. So the design is influenced by the manufacturing process. It's always that's the case. For example, all you see the nice curves and smooth surfaces. That's possible because some design cost has been incurred in. So always engineers prefer very straight surfaces, right? So that's how it is easy to manufacture, very less costly. The moment you make it more complex, the design is more complex, intricate parts, interchanging parts, right? And all those things, the parts which are relative motion, it's going to be a little costlier. So now people look at design from a two different point of view. One as opportunistic, another one is restrictive. So what is an opportunistic? For example, so restrictive is about ability to look at the design and say which is not possible. Opportunistic is looking at the design saying what is possible. So there are two ways of looking at a problem. One is you take a design and say, yes, this design is not possible, not feasible. And you can also say that this design is possible in something else. So design for additive manufacturing is usually about the opportunistic approach, wherein you can take the design, instead of telling that, let's say, for example here, you have to add a draft angle. If you are, let's say, this is a die casting process, this is the pot. So, excuse me. So this is a die casting part. So you need to provide a draft angle so that it can be removed from the mold, dies. So there's a reduction in design space. And for example, the design freedom for 3D printing is very high. You don't have to provide any draft angles. So SLM is a selective laser melting process, which is the 3D printing or additive manufacturing process. And also in injection molding, you have to maintain a uniform wall thickness. Here you don't have to maintain a uniform wall thickness. So the design freedom is very high. So also the weight reduction, you can have thin, thick cross sections. And the undercuts is not possible in conventional process, whereas in additive manufacturing, you can consolidate them together and you have very high design freedom. So like that, you can go on discussing about such comparison. So you have variety of design rules which have been made thinking about the process by which the particular design is going to be realized or manufactured. So today, so we talked about mass customization. I will also touch about a few aspects which helps you to basically customize the parts for individual needs. How do you customize a part? Let's say there are a variety of tools and techniques that are available where you can use these techniques and tools to basically customize your part. Maybe you can actually use multi-materials. You can use hierarchical structures. You can use heterogeneous type modeling. You can use lightweighting. You can use topology optimization. You can use generated design, or you can use part consolidation. So the techniques that we use to achieve, let's say, design freedom is like, or increase the complexity of the design, is what we call as design for additive manufacturing. It's like a collection of many different tools and techniques. Now let's just look at this design for additive manufacturing. Let's just look at what is mass customization. As I said, mass customization is customizing the design for personalization and flexibility, at the same time achieve the cost of low cost of mass production. That is the idea of mass customization. So how do we achieve a mass customization? How is it possible? How do I make sure that mass customization is achievable? Now let us just look at this particular slide. So there are many different tools and techniques to achieve this. Now, what are the tools and techniques that are used to basically, to achieve this part consolidation? The part consolidation is, I would say, is the ability of the design. You can actually have so many different parts. The only problem with large number of parts is the ability to basically make them and assemble them. So if you have a lot of issues in the assembly stage, just because you have too many parts, you can consolidate them. So 3D printing allows you to basically consolidate too many parts into one, and you are able to basically combine these parts together so that you can achieve one single part. So that we usually call as part consolidation. And you can also remove volume, like lightweighting and intricate lattice structures and other things. You can have heterogeneous materials, or you can have generative design, or you can have hierarchical structure. So these are various techniques. For example, hierarchical structure is about repeating structures in different scales. So maybe you have, let's say, a design where you have the same structures repeating in one scale, in another scale. But let's say you have a micro scale, meso scale, let's say macro scale. So the structure gets repeated I would say for every, I would say scale. So that means that you are able to get a very good strength as well as very good accuracy, just because you are able to basically customize your design tailoring to the needs of the particular application. Now, so I think we have discussed about all these aspects. So what we'll slightly differentiate the 3D printing to the conventional approach is that the ability to use three-dimensional CAD. As I said, 3D printing uses the direct digital representation. That's why it's also called digital manufacturing. Sometimes it's also called a solid freeform fabrication, or layered manufacturing, or additive manufacturing, or 3D printing. Now, one of the issues with the 3D printing is the ability to basically virtually you can print any geometry that you want. Means, like, let's say you have a powder-based process. If you are able to pulverize any material in the powder form, you can add a binder and you can always make it. People are made with too many materials, so you have a material freedom. You can use many different materials. Right now, the commercial materials are very limited as of now, but in the lab scale, people are trying to develop too many materials nowadays. But material freedom is there, and design freedom is also there. And you also have geometric freedom. So the ability, so conventional geometry that are not possible is the ability to fabricate. So the complexity with which this geometry varies is what we are looking at. For example, if you look at the lightweighting, so previously people used to machine huge amount of material from the, I would say, material, so that they can actually lightweight it. Lightweighting is very essential for achieving material efficiency, as well as in the use case you can achieve other efficiencies such as fuel efficiency if it's a car and or aircraft and things like that. So you are able to get a good amount of material efficiency, or I would say energy efficiency, or maybe even other efficiencies, if you are able to take material out of it. So lightweighting, you can use lots of lattice structures, intricate lattice structures, which could reduce the weight. And it could be tailored. This is what I was talking about, customization. You can tailor the structures wherever it is needed. For example, previously when people design, they don't know where the stresses actually are and where the material. So because of the limitation in the manufacturing process, they would put material everywhere. Whereas if you see, the topology optimization is about optimizing this layout of the material. So if you know where your stresses flow, so you can optimize the material, and so that the material that can be there only where the stress flows. In other regions where it's not functional, it could be removed. So for example, you can optimize the material layout for a given design space and a given set of loads and boundary conditions and constraints. So this is essentially called as topology. And you also have generative design. The same topology optimization can be subjected to manufacturing constraints. For example, when I'm optimizing the geometry, I can tell you that you can optimize it for additive manufacturing. Now, so I have been trying to paint a good picture about 3D printing so far, but 3D printing also have some issues. Now let us just come to the first issue. One of the issues with 3D printing is that it is also having support structures, like jigs and fixtures. As I said, machining needs jigs and fixtures. Very similarly, it's like you can say that if there is an overhang and a part need to be built, there could be support structures. So in order to eliminate the support structure, what people try to do is they always try to orient the part in such a way that the support structures are eliminated. Now, so you can add an additional constraint when you are trying to optimize materials for topology optimization. You can add an additional constraint. So let's say I want to eliminate all the supports. So can you just do it? So support structure is something like, let's say when you're trying to build the part layer by layer. So there could be some layers, right? So there could be some layer which just like that's an overhang that is hanging in space without any support from the bottom. So you are printing layer by layer, and suddenly one layer at top which is having no supports from the bottom. So for that parts to be built successfully, you have to build supports from the bottom. I think support structures are essential when you have overhang surfaces. Now to eliminate that, you can optimize the geometry in such a way that it eliminates the support structure altogether. So those are the things that we are doing. I'll just quickly give you an overview of what this deform tools, and especially about, I'll spend a little more time on mass customization here. So part consolidation is the ability to combine different parts and manufacture them together, because one of the very important topics in DFM, design for manufacture and assembly, is DFME, the conventional DFME approach, is you need to reduce the number of steps that are required for assembling the parts. So at the same time, you need to take care of the concerns in servicing aspects. For example, you need to remove the parts sometimes for and maintaining the parts at the use case of the life and things like that. So essentially, but in general, the principle is like reduce the number of parts. So you can combine many different parts. So those things can be looked at here. So you can combine many different parts into one. So you can achieve the part count reduction. That is only ease of assembly. Excuse me. Conventionally, it may not be possible, but additive manufacturing makes it easy to do this. Okay, so mass customization. Let's say we have been looking at mass customization from a variety of different angles, but when we look at the end applications, so the one that you see in the background color, so this is like all parts of different designs. Now, let us say when you want to let's say for example iterate using a generated design is an automatic procedure to generate alternative designs. Let's say if you want 1,000 designs or 1,000 variations of the same design, so it can be generated by using artificial intelligence techniques. Let's say you have artificial intelligence technique and you are able to basically learn from the design constraints and design techniques, and then you can generate varieties of design alternatives. Let's say you have one design, but it could be generated into several hundreds of designs. Now each of them can be manufactured. Like for example, I'll give you some basic idea about some medical application, and then probably I'll tell you about generative design and what it is and how it can be used and things like that. So now mass customization is like when you are looking at personalization. So for example, this is a case study which you might be aware if you have attended previous lectures. I used to tell this case study in many of my lectures. So if you look at this particular part, this part is a very simple hearing aid shell. So the hearing aid shells are usually manufactured by either injection molding or probably you have a different process. These are in the canal hearing aid shells. So if it's not fitting exactly into the ear and the person with hearing impaired, he may not be able to wear it properly. He may have some difficulties. So what people do is you need to make individual designs for individual person because individual person's cavity are different. So the canal geometry needs to be captured. The canal needs to be captured. The design of the canal needs to be captured. So let's say you go to a doctor. The doctor scans the canal for 100 patients in a day, and then produces a nice shell around it. Then you can put electronics into it and then assemble a hearing aid. Right. So to do that, so if there are 100 designs, you cannot make 100 modes, which is going to be expensive. So, but if you have a 3D printer or additive manufacturing machine, so you can actually make all these parts together. So essentially, it is about the ability for making, let's say, 100 designs overnight without having to machine a mold or without having to have a jigsaw fixture. So that is what we call as the ability of mass customization as well as mass complexity as well as what we call as mass ability. Now, so let's just look at here. This is another case study, which is like drilling holes. So you have a jigs, which could be manufactured. This is a jig in medical field. Suppose if somebody is going to do root canal treatment and then fix an implant, so you have to drill that holes. But the problem is that when you are drilling holes, each hole is of different orientation, and each, I would say, drill depth is different. So how do you basically design a jig where I can drill different depth of holes and different angles? So I need a fail-proof or fail-safe way of doing this particular, I would say, task. So 3D printing can come to rescue. For example, one of the ways 3D printing helps is to take the geometric CT scan and design a nice shell around. So you can see the nerves which is going through the teeth, and then you can design a jig which allows, let's say, for example, each of these holes are a different orientation. At the same time, each of the holes are different depth. So you are able to design a fixture where you can drill a hole and then fix an implant. So you are able to customize. This is for individual patients. So each patient is going to basically designs. So do you understand that? So that's now. So as we progress further, you see that we are able to basically design customized for individual needs, but at the same time, you can also tailor properties. You can customize the properties within the material. So we are talking about personalization. Personalization is the ability right? Personalization is the ability to change the design according to the needs of the human, right? So, but is there a way to customize the design according to the function? Let's say, for example, you need a part which has different functions. I think nature does that very nicely. For example, if you take our bones, the bones are strong enough at the edges, whereas if you go to the center of the bone, it is like we have different regions of the bone. The marrow region of the bone is not that dense. The density of the marrow region is very, very less. It is because it can actually transport. It can transport, right, materials and nutrients through that. So that's why you have different variation in the property. Even if you take a bamboo column, so you see that you have different gradation in property because nutrients has to be transported at the edge. But at the edges, it could be very strong. At the center, it could be very weak. So you see that variation or the customization of the design with respect to function. So that is what we call as functionally gradient structure or functionally gradient materials. So the ability to design something which basically varies over the function. So that we call as the porous structures or foams or custom designed foams, or we can call as tailor-made. So what do you mean by tailor-made? I think is a very important word that you all hear. So tailor-made means like you have ready-made and tailor-made. I think when you go to a shop, you get different sizes. You have XL, double XL, right? So when you buy a shirt, but when you go to tailor, so the tailors can actually measure unique dimensions according to you, and he can stitch something which is very unique for you, which fits exactly to you. So very similar. These are tailored structures where you are customizing the needs. Let's say, for example, if somebody wants to look at this particular design, here somebody wants a very dense outer thing, whereas less dense at the inner region. Let's say he wants to transport something at the end, so probably it could be a cooling channel, or it could be something like maximizing the cooling, or it could be a heat exchanger, or it could be something like a foam, right, which is used for several purposes. So the thing is, like, you can see customize the design. So you are able to change the properties or porosities, intricate lattice structures. You can do lightweighting at the same time. So let's say you have a structure. One of the ways to achieve this is you just first make a foam. Maybe you can do it in any foam. Let's say you take a simple injection molding pot. In injection molding pot, so in injection molding pot, what you do is you use a supercharging fluid and then create a nice cellular structure or cellular foams. Right, so which is lightweight, which has interconnected pores inside, or sometimes it may not be interconnected pores, and essentially you are able to achieve a lightweight reduction. Right, so that is one way to achieve lightweight. But you cannot control the pore size and pore diameter. But what you can do is, if you have a conventional way of making this different gradation in the porous parts, make 10 parts of them, do a CT scan, get the geometry. Like for example, these are the geometries scanned from the original or conventional manufactured part. Let's say you have a 3D printed part, you can actually design with your units. So for example, these are hexagonal units which are designed, but these structures are just scanned from an existing porous structure. Then you can do a Boolean. So let's say you have a volume in which you want to fit this unit cell. So you can actually fit the unit cell. Excuse me. You can fit a unit cell inside that so that you can find the gradation in different properties. So this is a kind of customization or personalization, I would say, for the functional. So this is the functional complexity. You are able to vary the material property. You can also vary the material composition. So we call this as compositional heterogeneity. So let's say, for example, you want certain materials in certain positions, certain function in certain positions, certain behavior in certain parts. So if you are able to understand the material thoroughly, especially from the process, structure, property, function, behavior, correlation. So if you are able to completely get that loop, you will be able to tailor many different functions, properties, behaviors in the part through additive manufacturing. So that is why 3D printing helps in mass customization. So this is an example of topology optimization. So what is topology optimization is, now here we are looking at lightweighting. So or we are looking at the way to reduce the cost. So there is a very important topic in 3D printing that we call as what we call as this powder bed fusion process. In powder bed fusion process, essentially we use a laser beam. The laser beam, usually we use 200 to 300 watts for a metal and 50 to 60 watts for a polymer. So most of the metal powders that are successfully 3D printed now are Inconel, steel, even other alloys like cobalt chrome and aluminum and titanium and all those alloys. So they have been commercially successful. They have been manufacturing parts out of that. So one of the issues with these materials, especially the titanium and other materials, they are extremely costly. So aerospace industries, they call this as buy to fly ratio. So when you are buying something, when you are taking it to conventional route, let's say you are machining a turbine blade from from a big stock of titanium, so you are wasting too many material as a chip. So you are wasting so much material as a chip. So instead of that, if you can build, let's say, a part with 3D printing, so you are only building the near net shape. So you are eliminating the need for wasting the material as a chip. So essentially, you are able to measure material efficiency are very high buy to fly ratio, because these materials are costly. You know how the size of aero engines look like, and titanium blades and titanium casing and things like that. So they will be extremely costly. So essentially, if you are able to reduce the cost by cutting down the unwanted loss because of the chip production, so you can go to additive manufacturing. But still, it has got a lot of issues. You cannot, the flight worthiness of these components is yet to be approved. Many components they have been able to approve, but still long way to go. But this topology optimization is the ability to basically take out the material and optimize the material so that you can increase the design complexity. At the same time, you can actually achieve what you call as this material efficiency. So here, this is the starting design of a manifold. This is the final design of a manifold. You are able to take out the material and reach to a point where you have completely optimized the design, not just from the viewpoint of material, also from the cost, and also function. So that is the, for example, this would be less cooling if there's a cooling functionality also with it. So this would be more, you can have more cooling surfaces because it's conformal. You can have a conformal cooling channels and things like that. So you have a variety of topological optimization techniques which could be employed. So this is the basic step. Let's say you have a link like this, you want to topologically optimize. You can actually find out the part which is to be optimized. This is the final optimized parts. So you can see how the part changed from this to this. This is the topologically optimized final part manufacturing. This is the steps in topology optimization. You start with the 3D model, and then you have to de-feature the parts. Now, right now, you would have seen that there are too many holes being machined here. These holes are typically machined just to do the weight reduction. Remove those holes which are only for weight reduction. It's because we are going to do the complete weight reduction here, which is called de-featuring, and then define the areas which needs to be preserved, define the areas which needs to be where the material needs to be optimized. Then you create an ideal shape where the stresses flow, and then you finally get a component from like this. So this is the component. From this component, you are able to get to a component like this. And further, you can even do weight reduction by introducing lattice structures. That's what we are saying. So the ability to utilize topology optimization to start from a design, which is a conventional design. I think all of you agreed to the viewpoint that this design is primarily because it is to be machined. When you are trying to machine, you see that they kept these straight pockets. So these are pockets, these are holes, and there are steps and there are profiles. So you see that in a single CNC milling machine with multiple setups, they must be able to machine it. Or probably if they have a near net shape from a casting, they can machine it, or maybe in a die casting, depending upon the size of the parts and how it is manufactured. We have a primary process and then machining, and then subsequently grinding and all those processes. So essentially, we have eliminated the complete primary secondary process. We just do a powder particles. Then from the powders, we are able to basically understand how this particular part can be optimized from this to this. So because of the, now you can see the design complexity and the shape, as well as the material efficiency and everything which is achieved just because you are able to optimize the topology. Topology optimization is not new. It has been there for last 30 years, but still now the tools and techniques that are available today in the market, commercial market, you can do a very good topology optimization like this. So I'll just give you a brief example about how a generic design works, and then we'll look at further hierarchical and other structures, how it can be carried out. Right, so in topology optimization, what we have done is like we have defined the material space, because if you look at here, we started with the initial design. So this is the initial design. We said that you fill that space with the material, right? So that is what we are seeing. So this is the de-featuring. Now we're told that you preserve these spots where there's an interaction, where there's a shaft which is coming in, probably maybe there is a anchoring using fasteners here. So we told them not to touch these spots. We have a defined preserving geometries. We have defined geometries which needs to be optimized. So they have the initial solution. Whereas in general design, for example, in general design, this is how the input is. We don't give any, this is the starting design, but we don't give the starting design there. So, but we'll define the preserving geometry and the negative geometry. A negative geometry is like a geometry which need not, which doesn't need to be optimized. So where the material cannot flow. So in topology optimization, we are solving, let's say, we are trying to minimize the compliance. We are trying to optimize the solution by understanding the current load profile where the material actually stress flows and where the material needs to be kept there. But in general design, what we do is we do the same thing, but here we define something known as a negative geometry where we do not want the material to be. And we allow the material to flow in most of the directions around that. Right. So in that way, you are able to basically identify, I would tell that many different solutions that exist within that point. So there may not be only one single solution, but there could be many different solutions. That is how you can customize the design. So the ability to customize the design based on automatically, based on, like the layout, just the material layout. So you can actually have hundreds and thousands of designs. I'll show you the variations in designs that have been generated. For example, you gave a mass target, like I want to reduce 1.5 mass from the spot. So essentially, we are able to basically get so many different variations of the design, too many variations without having, let's say, individually sit and optimize each and individual design. So you are able to customize, you are able to optimize, you are able to generate so many variations of the design by just simply using topology optimization with, I would say, general design principles. Now you can see that there are many different outcomes. There could be a very important decision making tool that could help someone to identify out of all this which one will work fine, or maybe you can choose 10 and then identify a customer who likes this one design or a second design or a third design. You can choose 100 designs, and 100 designs can be manufactured for 100 different aircrafts. So this is the idea of, let's say, mass customization, the ability to make same variations in the design, but functionally it's the same. But you can see different geometries could be produced for the same design. So like you can see here, so there are hundreds. You are able to hit the variety here. So the volume is also high, the varieties are also high. Each part is completely different. So why do we need to do this? So because conventionally you may not be you may not be able to basically look at I would say this particular design and say, okay, if I want to manufacture this, let's say 15 designs, I would need the cost for each would be very high because you are one-off designs. Like let's say, for example, you are making only one part in conventional manufacturing, the cost of it is less. That's why general design, you can make 100 designs, so you can actually make them at one go. You can nest these parts in a one build platform, and all these parts can be made in overnight within 24 hours, depending upon the total build height. You can build this entire different designs in one night, or let's say in one day, or maybe 2 days, depending upon the total bounding box dimensions of this particular design. Now, as I was talking about, lattice structures and bamboo culm and things like that, you can also have heterogeneous objects. Like for example, as I said, you can design gradient structures. You can put material where you want. You can tailor the properties. This is customizing the properties. We have said customize the design based on the personalization. This is about customizing the properties. Let's say you want certain properties in certain regions, you can do that. Or certain materials in certain regions. Now, most of us have seen that, if you take a simple toothbrush, the toothbrush, you must have seen that when you are trying to grip the toothbrush, there are some elastomers and there are hard plastics, and the bristles are usually elastomers. So, or what you call fibers, right? So, when you have an elastomer, the body is made of two materials. When you have two materials, they have an interface. Like, for example, how do you make, like, let's say, I don't want to name a brand, you take a brand like Oral-B toothbrush. Like, you have a hard plastic, you have a soft elastomer. So both of them has to be having a good bonding. So people would have tested these two materials. So let's say you have an injection molding machine. First, inject, let's say, a ABS plastic and get the handle for the toothbrush. And the gripper, the elastic gripper, you can do a multi-stage injection molding. Or in one single mold itself, you can inject two materials. That is also possible. There are varieties of ways in which that can be manufactured. But you said there is a clear boundary between two different materials. So it is not graded. Whereas in conventional approaches, let's say the approaches like what we see here in natural objects like bones and natural bamboo and all those things, there's a graded in property. They don't merge. Material merge nicely. So it's like there's a gradation. There's not a marked boundary, but actually they merge. So they have I would say a graded region where there's both materials exist together. So for example, this is one example of I would say, a part which is typically having a method to model such a thing. So you can actually get different material properties in different directions. You can see here, you have a part which is like having different variations. You can have two different materials. Let's say the dark green is one material and blue is another material. You can have a graded property. So you can say that they nicely merge into each other. It's not at one boundary, the green becomes the blue, or the blue becomes the green. So essentially, along the rail curves, these are called rail curves, you are able to basically get a nice variation of the property along this curve. So what is hierarchical complexity? In hierarchical complexity, you are able to design repeating structures. These repeating structures are in macro, meso, or nanoscales. And this could be, like for example, these are different scales. Each scales have the same repeating structure. So like this structure, it repeats itself in multiple states. This gives you really good strength, and this can be customized and tailored properties. This could be used to tailor properties. Now, for example, the way to build them is like you take some 0th order geometry, and you do the octahedron of octets, and then again the second order and again third order. So it feels like you are repeating the same geometry in multiple scales. If you go in one scale to other scale, you will see the same structure repeating. So that is basically a hierarchical structure. These are ways in which you can actually design. So there are design tools which are available right now. There are commercial software tools which are available right now to design something like this, where you can remove material. It's not lattice, but it's still it may look like a lattice, but still it's like a structure which is repeating in multiple scales. So the way to achieve this is like you take a simple original shape. You in level 1 you join them like this, and level 2 join them like this. You see the same simple square shape being repeated in multiple scales in multiple directions. So that's how you can actually create an hierarchical structure which could be generated design. Right. So here I was talking about the case study about turbine blades. If you remember, I was telling you that buy to fly ratio is important. We need to reduce the scrap that is wasted as a chip. Now, hybrid additive manufacturing is one ability to where you can customize the design, as well as one way you can also achieve material efficiency. Right. So as I said, you can actually take one single part that could be manufactured by both conventional CNC as well as additive. Now, I was talking about few issues. One of the issues that I told you is about, like when I'm trying to basically bring the conventional process into the additive, instead of making them more competitive, they could be, I would say, compatible to each other. So you are able to get two processes which are complementary to each other. CNC is like very costly, but what you do is there are certain functional performance like tolerances that are only achievable final machining, finished machining. So additive manufacturing may not give. So you combine the best of both worlds. So here in this case, they started with the deposition, the DED process, and then they could basically combine the milling process. You can see the milling, deposition welding, milling again, deposition again, milling. So you're able to get a thruster like part. So this is the ability to combine multiple processes into it. So this is what about material complexity. As I said, multiple complexity is possible. So we are looking at the complexity angle. We are looking at the variety angle. We are looking at the customization angle. This is about the complexity angle. In the material complexity, you can actually see that the compositional heterogeneity can be achieved. You have copper 100% at the core and nickel 100% at the outside. So you are able to get a gradual variation. See that 100% copper, then it becomes 90 to 100% nickel. So the transition from copper to nickel is not sudden at one boundary, but it is transition. So this is the ability which we call as the material complexity. And also it could be functional complexity, where electronics and other components could be embedded. Functional complexity is like, let's say when you are customizing, when you are design. So it should also solve the purposes for doing many things. For example, when you buy a mobile phone today, you want to do it everything. You want to hear music, you want to use it for calendars, you want to take pictures, you want to schedule meetings, you want to use it for navigation, GPS, and all those things. So many sensors. So essentially, when you are customizing design, when you are designing something, make sure that they do variety of function. For example, lubrication, cooling, thermal management, right? So probably you can also do structural functions, heat transfer, electromagnetic. So if you, and also electronics, maybe sensing, it could be a sensor. So you design something, you make something such that it could be multifunctional. So multifunctionality can be achieved. For example, if you have a porous object, it could be really good for lubrication. I think you must be knowing that powder metallurgy is the preferred route for making gears because it has a good lubrication property. The porosity, the inherent porosity present in powder metallurgy helps in some cases, especially for lubrication properties. So here you can tailor the porous structures. So essentially you are able to understand the regions, you are able to customize the design based on different functionalities. Let's say in some region where you want heat transfer, or some region where you want weight reduction, some region where you want electromagnetic interference avoiding, or some regions probably you have fluid flow, optimizing the fluid flow, or sometimes some places you want good surface finish. So some places you have a very good structural member. So the same design, when you are consolidating, you can actually add all these functions to it. For example, here this is a one design which has been optimized like this. So you have state cooling channels which are becoming conformal cooling channels. So the cooling and thermal management becomes very easy. Sometimes you can also combine a sensor in IoT and other things. You can virtually print a sensor. You can print a sensor, you can print an antenna, active passive devices. You can integrate so many different electronic circuits onto the mechanical parts itself. So those things are typically called as functional integration. So this is what we call as functional integration. So you have a forged part. Typically, this is what the conventional manufacturing process. So people, what they do is they usually machine it. So this is what you see. They're usually machining it for cost savings, right? So, but now you can actually fabricate an optimized part with, let's say, lattice structures and things like that, or hierarchical structures, and also functionally embedding electronic circuits and antennas, and you can see the antennas, sensors, circuits, everything integrated into the one single mechanical part. So you can 3D print an entire part, and it is fully functional. So you don't have to assemble, electronic circuits in it. You don't have to put an antenna. You don't have to put, say, a sensor. You don't have to even optimize it for weight saving, things like that. So essentially, it's about customizing the ability to customize the individual designs based on whatever need that you have. So this is a busy slide. I'll send. This is the one slide that tells you about what are the various, I would say, advantages of using this design for additive manufacturing. Now, if you look at here, so we have so far looked at 4 different complexities: functional complexity, form complexity, hierarchical complexity, and material complexity. Now, so mass customization, when we talked about, it's about the ability to basically reduce, let's say, the cost because of the variation in design. Now, all the restriction in design, which is like internal walls, ribs cannot be possible, wall thickness combination not possible, no need of draft angles possible in the conventional process is eliminated. Means you are able to get good form or geometrical complexity. You are able to get a large aspect ratios. You are able to get undercuts, even big cross-sectional changes. Variable radii is possible. So you are able to get too many advantages out of it. This is the idea of form complexity. So in hierarchical complexity, so like you have porous structures, you have mesoscopic structures, surface structures, low wall thicknesses, and things like that. So you are able to get very good hierarchical complex parts. And also continuous material transitions we have seen, like functionally graded structures, also multiple materials, like electronic and mechanical functional materials in one part, sensors and things. So you have different materials. And also you are able to get relative motions. So sometimes when you are trying to do a part consolidation, the conventional rule is that, when you are doing like in DFMA, when you are doing using a Boothroyd or other studies, you are able to basically get a relative motion. Suppose if you cannot eliminate a battery. For example, conventionally, when you are having a product, the battery needs to be a separate component, right? So the battery needs to be changed because it cannot be integrated. But right now, many cars they are printing batteries directly onto the surface, so you don't have to, you don't have to really embed these components at a later stage. You can bring them together. That's the idea. So you have functional consolidation, functional extension. One part does multiple functions. You can embed foreign components, as I said, sensors and things like that. So these are the value proportions, what you get out of it. So you have reduction of design space, improvement in isolation, improvement in heat transfer, improvement in energy absorption, improvement in ergonomics and things like that. So, and this is what more important. You are able to get the manufacturing, logistics, assembly, and quality, material, and maintenance and development. So every cost gets reduced. And put together everything, leads to sustainability. Means material efficiency. If you are able to, let's say, efficient with respect to material, energy usage, water usage, and cut down emissions, you are able to basically become environmentally sustainable. So the ability to address environmental issues through additive manufacturing, especially through cost reduction as well as environmental burden reduction, is also possible through additive manufacturing to some extent. Now, what are the limitations? So the limitations for this is like you have different strength, you have different surface finish, and different speed and cost. So let's say, for example, some of the participants from this webinar, they were also asking me the same question. So what is the mechanical properties? You are saying that this is possible. So I think I painted a rosy picture of the 3D printing, but 3D printing also has its own limitations. For example, 3D printing cannot print much higher speed, whereas injection molding can achieve very high speed. So the notion of rapidity, the rapid manufacturing or rapidity comes from the fact that we are able to basically combine the different designs into one, right? So, but the rapidity is essentially because we are eliminating the intermediate process called mold making or die making or fixture design and things like that. So that is how you are becoming cost. For example, you can skip the production sector if you have a CAD model. Today you have a CAD software, you build a CAD, suddenly you can take it to directly you can take it to production without having to design molds or fixtures or things like that. That is the idea. Maybe you have to design only support structures which can be automated, right? So in most cases, so that's why you are able to basically say it's a rapid manufacturing, but still its life cycle time is not that high, very low compared to conventional. For example, injection molding can be extremely fast compared to 3D printing. So speed is issue because we are making it layer by layer. Each layer takes 10-15 minutes. Each layer takes half a minute. So let's say you have a layer thickness can be something close to 50 microns. So essentially, let's say a part like 30-40 microns, 30-40 mm could even take hours to build. So that's the reason why it's little slow. So the speed is slow. Surface finish is also very poor. So that's a issue that we need to address. Surface finish needs to be improved. So there are many different ways surface finish can be improved. Parts can be taken to things like, let's say, shot blasting, or it could be subjected into painting or polishing or electroplating or even some other process. For example, process like binder jetting, it involves even much more post process. Probably when you take it out of binder jetting, you may have to take it through debinding because you are used to binder, and then infiltration, and then you have hard isostatic sintering, and then you further machine it if you want to achieve good accuracy. You see, it also involves varieties of other post-processing operation. That is the one limitation. So the limitation is strength, surface finish, speed, and cost. Right. So these are some of the various aspects. Right. So which is actually a limitation in the 3D printing. Right. So right now the parts that are produced are to be over designed. The reason is because when you are making parts layer by layer. So when you are talking about strength, the strength in the direction of the build is always poor. So then you have to redesign, or you can say over design, because your factor of safety is usually designated by the strength in the Z direction, because that is the poor. So because essentially you have to have a very high material. It's over design because you are designing on the weakest link, that is the Z direction. And cost wise, I already told you that right now, today, if you are hitting volume, as I said, if you are going for mass custom machine, 3D printing is not that cheaper. So injection molding is much cheaper compared to 3D printing. But for one or two parts, as I said, it's extremely, the cost benefit is there. But if you're able to achieve volume as well as variety at lowest cost, that is one issue. But still, there are a lot of patents which has not expired. So that's the reason why the materials are proprietary and the machines, commercial machines are proprietary, and the new materials are being developed, which are also becoming little, I would say, expensive to make. So material cost is expensive. Machine override is also expensive. So the cost aspects is still much higher compared to conventional manufacturing process. So these are the limitations. So the limitations are the improvement in surface finish, increase in the ability to produce thin layers, thin features, and the material properties and range and construction time. So these are the ways in which you can improve. So the improvements can be done in all possible ways. So I will take few questions from the Google chat, the Google Meet chat box, as well as on the YouTube live. So I will try to basically address. I will spend the last 5 minutes trying to address your questions. Right. So thanks. I will hand over the session to the professors at SVCE. Probably they can moderate the questions, and then I can pick up a few questions from there and try to answer whatever that I try to do. As I said, this is a full course, 40 hours course. Mass customization is the 3-hour lecture that we do. So essentially, we need to cover this in a full course. But no, I try to give a glimpse of what we do in that DFAM course. Hopefully, I'll try to answer a few questions. Probably, I'll hand it over to Professor. I think
Yes, sir. Yes, sir. Thank you, sir. Thank you so much. And this session is a wonderful session, and I can say this will be an eye-opening session for the many beginners and researchers in the additive manufacturing. And Professor explained the advantage of 3D printing technology, especially in the mass customization to reduce the cost. And also, he explained how the topology optimization can be done to reduce the weight and as well as cost. So thank you very much for your wonderful session, sir. And now, if any queries, participants, you can type on the chat box. And one of the questions raised by the one of the participants: is it possible to produce the components with metal plus polymer composites, sir, using 3D printing?
Okay, so it's a very interesting question. See, when you have two different materials, it is possible, but not, I would say, in a one single process. So metal and polymer, I would say, they have been mixed together and made. For example, the early machines which we had in 2000s, we had a material called alumide, which is aluminum plus polyamide. We have a material called copperamide, which is copper plus polyamide. We have a material which is mixed with metal powder, stainless steel plus polyamide. So we have mixed polymer powders and metal powders together. So it is possible. It has been like last 20, 30, almost 20 years people have been making parts, but I don't think it is a composite material. So these are done for a different purposes. It won't produce the same benefits of a composite material, but they are done for a different purposes. Right? So I think, for example, metal powders mixed with polymer powders are done especially to basically reduce the lightweight and making it lightweight and things like that. So, but it won't produce the strength properties of a composite. There won't be any intercalation, or I would say exfoliation, which you normally see in a nanocomposite, things like that. So essentially, you are going to get something, I would say, which is a mixture of two materials, but not really a composite.
Okay, sir. Thank you, sir. And another question. In case of casting, there is the big disadvantage is the porosity. And in the 3D printing, if there is any porosity, sir,
yeah, there are four major issues in metal printing. One of the issue we always discuss is like we have distortion, which is like part deviation. Second one is pores and porosity. So there is an inherent porosity in additive manufacturing because of the layering and powder usage. So, but sometimes you take the dissonant and convert into your favor. So people try to use, tailored porous structures for many different reasons. So porosity can be tailored. So it could be possible that the porosity can be used for, I would say, for constructive purposes.
Okay, so thank you.
But the porosity is, there are two types of porosity there. One is called gas-induced porosity. Another one is process-induced porosity. So gas-induced porosity you can actually eliminate by using vacuum. For example, electron beam melting process are usually done in vacuum where gas-induced porosity can be eliminated. Process-induced porosity can be eliminated by process parameter optimization. And there are a huge body of knowledge available for that.
Okay. And another question is, what are the important mechanical properties are to be considered for 3D printing components, sir?
Okay, so I think it's a very interesting question. So see, it depends upon the application that you choose. For example, many medical applications, people would like to have, deep flexural strength. Suppose if it's like applied in aerospace, people would like look at high temperature applications and creep resistance and then fatigue. So it depends upon application. But additive manufacturing, what properties is it really good at? It depends upon the material choice. It depends upon the processing method. It depends upon the material choice. So it's a very generic question, but I would say if you can specify one process, one material, and one function, I would say whether it is good or not. That's how it can be done. So, for example, compressive strength of an implant made in titanium, is it good? Yes, I can say in that way, but generically I would say that it is possible to understand the function, property, and behavior, and material, and process. So, if you know these relations, it will be able to tell us whether particular things can be processed, manufacturable to that accuracy and to that strength or not.
Okay. Thank you, sir. Another generic question. What is the difference between rapid prototyping and 3D printing, sir?
Okay, it's a good question. It is again about application. So,
Yeah.
like for example, when you are, let's say, using the 3D printing for product development purposes, like you are not, the part that you are going to produce is not finally going to be useful. So it's only for, let's say, trial and error or let's say prototyping purposes. So then it's called rapid prototyping. So essentially 3D printing and rapid prototyping, layered manufacturing, additive manufacturing, digital manufacturing, solid free-form fabrication, material incrust manufacturing, all these are different names. They are one and the same.
Okay. Okay,
Okay,
sir.
but the 3D printing is essentially given for polymers. Additive manufacturing is
Okay.
mostly used for metals, but that is also changing.
Okay, sir. And is there any ASTM standards for testing of 3D printed materials, sir?
Yeah, a lot of new standards
ASTM
have come
standard.
up. I think for strength, tensile strength, the ASTM has published new standards on additive manufacturing, and there are a couple of standards which are under development. So there are too many standards which are under development,
Okay.
but there are many standards which are already published. They are available.
Okay. Okay. Thank you, sir. Thank you
Thank
so
you.
much. With this, I would like to conclude this session. Thank
Thank
you
you.
very much for delivering the wonderful session on the 3D printing
It was
and
my
mass
pleasure. Thank
customization
you.
in manufacturing. Now, I would like to request one of the coordinator, Mr. A. Kumarasamy, to deliver the vote of thanks, sir.
Yes, sir. Yes, sir. This is Kumaraswamy, Assistant Professor, Sri Venkateswara College of Engineering. I would like to thank Dr. Senthilkumaran sir for his excellent presentation. And also, I would like to thank all the participants. In spite of their busy schedule in this lockdown period, they made their way to view this excellent webinar. And also, I would like to thank our beloved HOD, Dr. S. Ramesh Babu sir, who made this webinar possible. And also, he consistently encourages us to conduct this type of webinars. And I would like to thank our coordinator, Dr. Mohandas sir, for giving me this opportunity to coordinate this webinar. And and also I would like to thank our faculty and also our students who made their way to be present here to view this webinar. And also I would like to thank Airtel, who which made this possible in live stream in YouTube. Thank you, sir. Thank you. Thank you
Thank
so
you
much,
so
sir.
much, sir.
Thank you.
Dear participants, the feedback form has been already shared by Kumarasamy sir in the chat box. Make use of the feedback form. So once if you fill the feedback form, your e-certificate will be generated automatically. Thank you all. Thank you, sir. Thank you so much, sir. Thank you.
Thank you, sir.
Yes.